right, they tell me here on our definition of permutations that a permutation of n different elements in an ordering of the elements such that one element is first, one element is second, one element is third, and so on. A simple way of saying that is that when you are working with a permutation, the order matters. It makes a difference. As opposed to, in a few minutes, we're going to be talking about combinations. And when you have a combination, the order does not matter. It does not make a difference. Now, permutations are the exact same thing that we've been doing with fundamental counting principle. For instance, example 5. It says, how many permutations are possible for the letters A, B, C, D, E, F? So if I were going through and I were trying to figure out all the different ways that I could arrange those 6 letters, I would just draw 6 little answer blanks for myself. And I would say, okay, how many letters do I have to choose from for the first blank? 6, right. And then how many for the second blank? 5, and then 3, and then 2, and then 1, right? So something that they tell me here that's going to be a big shortcut for us is if you have, like in this case, you have 6 things to choose from and you're choosing all 6 of them, it's just going to be that number factorial. So if they ask me 10 things to choose from and I'm choosing all 10 where the order matters, it would just be 10 factorial. All right? Look at the next one, example number 6. Example number 6 says 8 horses are running in a race. And how many different ways can those horses come in first, second, and third, assuming that there are no ties? All right, so I'm going to draw for myself 3 little answer blanks. How many horses are vying for first place? 8. So there are 8 that could come in first. Then how many are left vying for second place? And then third place? So we could just say 8 times 7 times 6, and there would be 336 different ways that those horses could finish. We can come up with that exact same answer by using a permutation. So we can do fundamental counting principle like we've been doing, or we could use the new permutation formula that they give me. So the permutation formula they give me says NPR is equal to n factorial over n minus r factorial, where n is the number of things I have to choose from, and r is the number of things that I'm choosing. N is what I have to choose from, R is what I'm choosing. And you'll notice that formula looks remarkably like our NCR formula. The only difference is that little R factorial right there. Okay, so let's go back to our horse example again. How many horses did I have to choose from? 8. How many am I choosing? 3. And it was a permutation because the order mattered. If I'm the owner of the horse, it matters to me if my horse comes in first or third. That's a big difference. So order does make a difference here. So according to that formula, I would just say n factorial in my numerator and n minus r factorial in my denominator. So that would give me 8 factorial over 5 factorial. And we've been doing these factorial problems since section 9.1, so we know how to simplify them. But we could go through and say 8, 7, 6, 5, 4, 3, 2, 1 over 5, 4, 3, 2, 1. And we can even say 5 factorial instead of having to write out 5, 4, 3, 2, 1. Now here's the cool thing. If you'll notice, when I used that formula and I simplified, look what I have left. 8 times 7 times 6. That's the exact same thing we had up here for fundamental counting principle. They do the same thing. So for your permutation, you could use the little blanks and do fundamental counting principle, or you could use the permutation formula. So the permutation formula is really helpful if I have 50 things to choose from and I'm choosing 27 of them. I don't want to sit here and have to draw out 27 little blanks and count all the way down. It'd be a whole lot easier to use the formula. Plus, just like we had NCR in our calculator, you have NPR in your calculator as well. So grab your graphing calculator and let's make sure that we can do NPR. So we had 8P3. So remember that you have to put n in first. So I'm going to put the 8 in first, and then I'm going to do math and go over to probability. And so you can see there's the NCR that we've worked with and the factorial that we've worked with. We're just going to choose number 2, the NPR, and then we can put in 3, and there's that same 336. So you can see that whether I use fundamental counting principle or I use the NPR formula by hand or I use NPR on my calculator, I'm going to get the same answer. Okay. Now, on the top of page 668, they talk to me about distinguishable permutations. A distinguishable permutation is just a permutation that has repeated elements. What do I mean by that? Okay, come back up here to example number 5. In example number 5, they gave me 6 different letters, and they said how many different words, if you want to call them that, how many different words could you make out of these 6 different letters? And so it was 6 factorial. But if all of my letters aren't different, if I have repeated elements, repeated letters in this case, my formula needs to be different. Here's why. Let's say example number 7, the 6 letters that they give me are the letters in the word banana. If I'm looking at banana, if I take the first A and I switch places with the second A, that word is not going to look or read any different at all. I'm not going to count that as 2 separate entries. So I need a different way to attack this. I've got to divide out that repetition of those repeated elements. So I'm going to start the same way that I did up here at the top. In example number 5, I had 6 things to choose from. I was choosing all 6. That was 6 factorial, right? I'm going to start that same way. I have 6 to choose from. I'm choosing all 6. It's just going to be 6 factorial in the numerator. But in my denominator, I'm going to divide out that repetition. And so the denominator down here, these are going to be the repeated elements. So because I had 3 A's and I had 2 N's, I'm going to divide by 3 factorial and 2 factorial, and that will take care of that repetition. So if I simplify that, and we've been simplifying factorials again for several sections, so we're good at that, I get 60. Look at the difference. I had 6 different letters to choose from up here, and there were 720 different ways they could be arranged. I had some repetition down here with my 6 letters, and so there were only 60 different ways that they could be arranged. Unless you don't believe that there are exactly 60 different ways that you can rearrange the letters in the word banana, somebody who had entirely too much time on their hand actually wrote all of those 60 different configurations out on the bottom of page 668 so that you can see there are exactly 60 of them. That formula really does work. I'll take their word for it and use the formula and not have to write them all out and count. All right, so those are our permutations. Let's talk about our combinations. In a combination, the order is not important. So in a combination, I'm going to have one extra piece. I still have the n factorial over n minus r factorial that was in my permutation formula, but there's an extra r factorial right there. And again, that r factorial is going to serve to divide out repetition. Okay, so we're going to read a problem in the homework, and we're going to have to decide, is it a combination or a permutation, so I know which of those 2 formulas to use. So here are some examples, all right? Let's say that we are electing a president, vice president, and secretary of the junior class, okay? So if we're electing those 3 offices, the person who gets the most votes we're going to call the president, and then the person who gets the second highest votes we're going to call the vice president, and the person who gets the third highest votes then we'll call the secretary treasurer, okay? So it matters if I come in first or if I come in third. Order makes a difference there. But if I'm electing a 3-member committee from the junior class to represent us on the student council, it doesn't matter if you get elected first or if you get elected third, you're still on that 3-member committee to represent us to the student council. So that would be a combination. So president, vice president, secretary, treasurer would be a permutation. 3-member committee would be a combination. All right, here's another example. Let's say that I am hiring for a company, and I'm hiring a computer analyst, and I'm hiring a custodian for my janitorial staff. It matters if you get hired first or if you get hired second. There's going to be a big difference in salary and benefits and hours and that type of thing. But if I'm hiring 2 data entry clerks that are going to have the exact same hours, the exact same salary and benefits package, they're going to work in the exact same office, it doesn't matter if I get hired first or second, it's still the same thing. So the computer analyst versus the janitor is a permutation, whereas 2 equal data entry clerks is a combination. All right, what if you are inviting 5 people to a party? Is that a combination or a permutation? Does order matter? Combination, right. It doesn't matter if you get invited first or you get invited fifth, you're still going to the party. It might hurt your feelings if you get invited fifth instead of first, but you're still going to the party. It's a combination. If we said how many different ways could we arrange 3 math books on the shelf? I have a calculus book, a pre-calculus book, and an algebra 2 book. How many different ways can I arrange them? Permutation or combination? Permutation, right, because calculus, pre-calculus, algebra 2 would be counted separately than algebra 2, pre-calculus, calculus. That's 2 different arrangements. It's going to be counted separately, so the order would matter. What if you are dealt a 5-card hand from a deck of 52 cards? Your 5-card hand, is that combination or permutation? Combination, right. Because if you're dealt an ace as your first card or you're dealt an ace as your 5th card, it doesn't matter. You still have an ace in your hand, right? I mean, most of the time we pick up our cards off the table and we rearrange the order of them anyway. So that would be a combination as well. So again, that's what we want to do is on the homework, we want to look at the scenario they give us and decide, is it combination or permutation, and use the appropriate formula. Now, here's the difference in that formula. We said that difference in that formula is R factorial, where it's just going to divide out the repetition. Let's go back to our president, vice president, secretary idea up here, okay? So let's say that we have John and Sue and Amy as the 3 people that we're looking at, okay? I could go through and I could rearrange John, Sue, and Amy in several different ways. I could do John, Sue, Amy, Sue, John, Amy, Amy, Sue, John, John, Amy, Sue, Sue, Amy, John, Amy, John, Sue. That's every possible combination. There's 6 of them, right? So look at the difference between these 2 formulas. What this formula says is, if the number of people you're choosing, in this case we were choosing 3, if the number of people you're choosing, the order doesn't matter, I've just counted those same 3 people 6 different ways, right? So that's what I have to get rid of, that repetition in my combination formula. So if I were choosing 3 people, the difference in that formula would be that R factorial right there. It would be 3 factorial. What's 3 factorial? 6. All that R factorial does is just divide out the repetition. It divides out the number of ways that I could rewrite that same 3-member committee. Okay? So your combination answer is going to be significantly lower than your permutation answer typically. That's another way that you can kind of double check yourself. All right, look at example 8. Example 8 says, in how many different ways can 3 letters be chosen from the letters A, B, C, D, E if the order of the 3 letters is not important? They pretty well spelled that one out, right? Order of the 3 letters is not important, so we know that's a combination. So we had 5 letters to choose from, and we're choosing 3. So we're going to go back. That's the exact same formula that we were using for our binomial coefficients in the binomial theorem. It works the same way. So whether we worked it out by hand or on our calculator, we would come up with 10 different orders when the order is not important. 10 different combinations. All right, look at example 9. Example 9 says, a standard poker hand consists of 5 cards dealt from a deck of 52. How many different poker hands are possible? Permutation or combination? Yeah, we already talked about that would be a combination. It didn't matter if your ace was your first card or your last card. It's still in your hand. So how many do I have to choose from? And how many am I choosing? All right, so we could again just apply that formula the same way we've been doing it all week long. And we would be able to come up with the total number of possibilities